Atoms attach to one another in various geometric arrangements. The overall molecular shape of a molecule is determined by its bond angles in 3 dimensions. The shape of a molecule is very important for its physical and chemical properties. VSEPR theory, or valence shell electron pair repulsion theory, is a method for predicting the shape of a molecule from the knowledge of the groups of electrons around a central atom. Electron pairs, bonding and non-bonding electrons, repel one another. As a result, the electron pairs remain as far apart as possible from another to minimize the repulsion. The repulsion of lone pair electrons is greater than the repulsion of bond pair electrons. This will become important later when we determine bond angles. Now, how do we apply VSEPR theory to determine molecular geometry? First, we draw a plausible Lewis structure of the molecule or polyatomic ion. Then, we determine the number of unshared electron pairs and number of bonds around the central atom. Multiple bonds count as a single bond. This will become important later. Then, we establish the geometrical orientation of the electron pairs around the central atom as either one of the following electron geometries: linear, trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral. Then, we describe the molecular geometry. Let's begin with our first VSEPR shape, when we have two things around the central atom. Our first example is going to use beryllium dichloride. There are only two places in the valence shell of the central atom in beryllium dichloride where electrons can be found. Repulsions between these pairs of electrons can be minimized by arranging them so that they point in opposite directions. Thus, the VSEPR theory predicts that beryllium dichloride should be a linear molecule with a 180-degree angle between the two beryllium chloride bonds. To make this more clear, it may be easier to picture covalent bonds as if they're hands from the atoms with electron pairs, and that these hands are connected because they're both holding on. They're both sharing this pair of electrons. So we could draw beryllium dichloride like this, where we have a hand from the beryllium, a hand from the chlorine coming together to hold or to share this pair of electrons. So this just further reinforces the idea that there's a pair of electrons in each one of these bonds that is shared between the atoms. Compounds that contain double and triple bonds raise an important point. The geometry around an atom is determined by the number of places in the valence shell of an atom where electrons can be found, not the number of pairs of valence electrons. Consider the Lewis structure of carbon dioxide as an example. There are 4 pairs of bonding electrons on the carbon atom in CO2, but only 2 places where these electrons can be found. They are electrons in the CO double bond on the left and on the right. The force of repulsion between these electrons is minimized when the 2 CO double bonds are placed on opposite sides of the carbon atom. The VSEPR theory therefore predicts that CO2 will be a linear molecule just like beryllium dichloride, with a bond angle of 180 degrees. Thus, whenever we have two things around a central atom, we have a linear shape with a 180-degree bond angle. Now let's move on to when there are 3 things around a central atom. There are 3 places on the central atom in boron trifluoride where valence electrons can be found. Repulsion between these electrons can be minimized by arranging them towards the corners of an equilateral triangle. The VSEPR theory therefore predicts a trigonal planar geometry for the boron trifluoride molecule with a FBF bond angle of 120 degrees. Sulfur dioxide also has 3 things around it, except unlike boron trifluoride, which has 3 atoms surrounding the central atom, this time sulfur dioxide has 2 atoms surrounding the central atom and 1 electron pair. Since lone electron pairs exert a higher electron density on the other 2 bonds and strain them more, the actual angle is not the classic 120 degrees and is actually slightly less, usually approximately 116 degrees. Thus, we call this VSEPR structure bent. Lone electron pairs will come up in other structures, so remain aware of them. Now let's move on to when there are 4 things around a central atom, like in methane. In molecules with the central atom surrounded by 4 bonding pairs, if we consider the central atom is placed at the center of a sphere, then each of the 4 pairs of electrons will occupy a position to be as far apart as possible. This will result in the electron pairs being at the corners of a regular tetrahedron. Therefore, these molecules are said to have a tetrahedral shape. The angle between each bond will be 109.5 degrees. In molecules with the central atom surrounded by 3 bonding pairs and 1 non-bonding pair, also known as an electron pair, we will have a shape known as trigonal pyramidal. Due to the repulsion, a non-bonding electron pair requires more space than a bonding pair. The angles in these molecules are 107 degrees, not 109.5 degrees, as in the tetrahedral molecules. We can see this exemplified in our ammonia molecule. In molecules with the central atom surrounded by 2 bonding pairs and 2 non-bonding pairs, as is seen in H2O or water, the 4 pairs of electrons will be arranged tetrahedrally, but since only 2 pairs are bonding electrons, the surrounding atoms are at 2 corners of the tetrahedron. As a result, these molecules will have a bent shape. The repulsion between the non-bonding pairs will result in a bond angle of 104.5 degrees. For each pair of non-bonding electrons, the bond angle decreases by 2.5 degrees. Now let's move on to when there are 5 things surrounding a central atom. Like in all VSEPR shapes, molecules with the central atom surrounded by 5 bonding pairs will arrange themselves with their electron pairs as far apart as possible. To achieve this, the atoms will arrange themselves in a trigonal bipyramidal shape, which consists of 2 pyramids sharing the same base. In this type of molecule, the 3 atoms making the base will lie in the same plane with the central atom in the middle of it. The other atoms will be positioned above and below this plane. The bond angles within the base will be 120 degrees, and the bond between the other atoms and the base will be 90 degrees. This is clearly seen in our example of phosphorus pentachloride. Note, when there are 5 occupied areas, there are 2 types of axes. There is the axial axis, which goes ups and down, and there is the equatorial axis, which goes side to side and front and back. It is best for the electrons to be in the equatorial positions. When we extend the VSEPR theory to molecules in which the electrons are distributed towards the corners of a trigonal bipyramid, we run into the question of whether non-bonding electrons should be placed in equatorial or axial positions. Experimentally, we find that non-bonding electrons usually occupy equatorial positions in a trigonal bipyramid. To understand why, we have to recognize that non-bonding electrons take up more space than bonding electrons. If the non-bonding electrons in sulfur tetrafluoride are placed in an axial position, they will be relatively close, 90 degrees, to 3 pairs of bonding electrons. But if the non-bonding electrons are placed in an equatorial position, they will be 90 degrees away from only 2 pairs of bonding electrons. As a result, the repulsion between non-bonding and bonding electrons is minimized if the non-bonding electrons are placed in an equatorial position in sulfur tetrafluoride. In molecules with 4 bonding pairs and 1 non-bonding pair, when the non-bonding pair of electrons on the sulfur atom in sulfur tetrafluoride, as an example, is placed in an equatorial position, the molecule can best be described as having a seesaw or teeter-totter shape. This results in bond angles of just under 120 degrees. In molecules with 3 bonding and 2 non-bonding electron pairs, repulsions between valence electrons on the atoms can be minimized by placing both pairs of non-bonding electrons in equatorial positions in a trigonal bipyramid. When this is done, we get a geometry that can best be described as T-shaped, as is seen in chlorine trifluoride. The bond angles here are under 90 and 180 degrees. In molecules with 2 bonding pairs and 3 non-bonding electron pairs, when the 3 pairs of non-bonding electrons on this atom are placed in equatorial positions, we get a linear molecule with 180 degree angles between the atoms. In molecules with the central atom surrounded by 6 bonding pairs, in order for the 6 pairs of electrons to be as far apart as possible, in this case, each bonding pair will be at one corner of a regular octagon. The central atom is at the center of a square plane made up of 4 atoms, and the other 2 atoms will be placed above and below the plane. All bond angles will be 90 degrees. In molecules with the central atom surrounded by 5 bonding pairs and 1 non-bonding pair, The non-bonding pair replaces one of the atoms in the axial plane. This results in bonding angles being not exactly and just under 90 degrees. We call this square pyramidal because the atoms in the square plane make up the base of a square pyramid. In molecules with the central atom surrounded by 4 bonding pairs and 2 non-bonding electron pairs, the second non-bonding electron pair replaces the second atom in the axial plane. This leaves us with only atoms in the single square plane with the central atom at the middle. Since this only has one plane, we call this a square planar VSEPR shape, and all angles are 90 degrees.